Hi, everyone, and welcome back to our course on fusion energy. My name is Sophia, and I'm a current grad student in the Columbia Plasma Physics Lab. And today I'll be discussing electromagnetism, which is probably the most physics-oriented course of our lecture series. And will give us the necessary background to understand first plasma physics, and then how plasma physics relates to how we're trying to do fusion energy on Earth. So as an overview of what we'll be discussing today, we're going to start off with a quick review of vectors, because this is an important math concept for fully grasping electromagnetism. Then we're going to get into how electromagnetism fits in the grand scheme of all the fundamental forces on Earth and why we care about it. Then we'll get into a little bit of the actual physics of first focusing just on electrostatics, and then we'll discuss magnetism. And after talking about them both in isolation, we'll bring them together to learn about how electricity and magnetism are actually really one and the same and how they can affect one another. And then finally, we'll touch on a few of the applications of electricity and magnetism in plasma physics. However, next week you'll have a whole lecture on plasma behavior in electric and magnetic fields. So it's kind of a sneak peek of what we'll be discussing further on in the course. Okay, to start off, a quick review of vectors. So you may have heard this before. A scalar is a quantity with only magnitude. That can be something like mass, how heavy an object is, or length, like how long a ruler is. These are just numbers without any specific direction. We can also have vectors, which are a combination of a magnitude and a direction. So, for example, for a force, you care not just about how much force you're applying, but what direction you're applying that force in. And the same goes for quantities like acceleration. It doesn't matter just how much you're accelerating, but also where you're accelerating. So every vector has a magnitude and a direction. And we can usually tell when a quantity is a vector because the symbol will have a little arrow over the top. So in this presentation, any quantity with an arrow is a vector. There's also a specific type of vector that's really useful for notation. So a unit vector is a vector with a magnitude of 1. So it doesn't have any magnitude scaling, and it only tells you about direction. And these vectors are usually written with a little hat or caret symbol above them. So I've listed here a few really common unit vectors in physics. I with the little hat usually means the x direction. J with the little hat usually means the y direction. And then we also have more complicated unit vectors like R with the hat, which would mean just like radially outward from a source. So we can use these vectors, these unit vectors, to tell us about direction. For example, over here we have the acceleration vector, which is listed as 5 I hat. That basically means the acceleration has a magnitude of 5 in the x direction. So the unit vectors don't change the magnitude at all, they just tell us which way we're pointing. And you'll see these unit vectors a few times in today's presentation. Finally, one of the more complicated concepts we have to talk about today is a vector field. So vector fields are everywhere in physics, and what it essentially means is that for every point in physical space, any location you might be in, the vector field has a specific magnitude and a direction. So a lot of times we show these in representative plots like the ones below. At every point, you can see we have an arrow, and the size of the arrow denotes how strong the field is there. And then the arrow tells us where the field is pointing at that position. So this is also something to keep in mind because we're going to talk about a few different vector fields today. And then finally, there's a few vector operations that we don't need to totally understand the math of, but it's helpful to understand conceptually because they underlie some of the main equations in electromagnetism. So first we have a dot product, which we show with this little dot symbol between two vectors. This operation returns 0 if the vectors are perpendicular to each other, but it's very large if the values are parallel. So it's basically a measure of how parallel your vectors are. We also have something similar called a cross product, which is shown with the X symbol. This is sort of the opposite. The cross product returns 0 if the vectors are parallel, but it's very large if they're absolutely perpendicular. And the cross product is a little bit unique because instead of just giving you a number to tell you how parallel or perpendicular the vectors are, it actually returns a new vector that's perpendicular to both of the original vectors. And we'll get into this a little bit more in the context of magnetism, how taking the cross product of two vectors gives us a totally new vector. Okay, cool. Now let's zoom out a bit to talk about what are fundamental forces in physics. So what some of you might know is that all forces in the universe can basically be classified under the heading of four termed fundamental forces that are sort of just inherent to the universe. And electromagnetism is one of them. But we'll start off by discussing the weakest of the fundamental forces, which is actually gravity. So the gravitational force, you probably all know about, it's an attractive force between all particles that have mass. So it's the thing that keeps our planets orbiting around the sun, keeps the moons orbiting around the planets. It's what keeps us down on Earth, and as well as our atmospheres. And what some people are surprised to learn is that it's actually the weakest of the fundamental forces. And the reason we still perceive it having such big impacts is because it acts on really, really big objects. So gravity can keep the planets in orbit because planets are really big and they have a lot of mass. But the gravitational force itself is extremely weak. So we're going to talk about all our other forces in comparison to gravity. Our next weakest fundamental force is actually termed the weak nuclear force. This is probably the most uncommon to hear about at a middle school and high school level, but it is 10 to the 32 times as strong as gravity. So even the quote weak force is way stronger than gravity. And its main role is participating in the radioactive decay of particles, which we won't get into a ton in this lecture. Our next force is the electromagnetic force, which is the topic of this lecture. It's 10 to the 4 times as strong as the weak force, 10 to the 36 times as strong as gravity. And it is the attractive or repulsive force between charged particles. So in formulation, it's very similar to gravity, with the main difference being that gravity is always attractive, it always brings things together, while electromagnetic forces can be attractive or repulsive, depending on the sign of the charge. And this electromagnetic force is used in a lot of human technology. It's all around us. And most importantly, it actually keeps the electrons orbiting the nucleus in all atoms. And finally, our strongest force is actually called the strong force. It's 100 times as strong as the electromagnetic force. And this is the force that binds the protons and the neutrons together in the atom. Because neutrons are electrically neutral, so they don't experience an electromagnetic force. So there's an extra force needed to keep protons and neutrons together in the nucleus. So now that we kind of have this context for the fundamental forces and how strong they are, we want to get into really what electromagnetism really is. Okay, cool. We'll start off with the concept that's a little bit easier to understand, which is electrostatics. Basically, how electricity acts without any time dependence, just in a static scenario. So electrostatics act on any object that has charge. Charge is a property of particles that basically makes them experience this electromagnetic force. And charges can be positive or negative. So protons are positive, electrons are negative. There are other particles, fundamental particles, that also have different charge. And charge is measured in a unit called coulombs. Another interesting fact about charge is that charge is actually quantized. So the smallest unit of charge is the electric charge, which is 1.6 times 10 to the negative 19 coulombs. And every other object must have a multiple of that number. You can't have 1.5 electric charges. You have to have an integer multiple of electric charges. And that was actually discovered in this experiment we have pictured here, the Millikan oil drop experiment, which you can read more about. But he basically discovered by charging oil or milk droplets that they always had an integer multiple of this fundamental charge. So that's kind of an interesting fact. Okay, now we're going to move on to talk about our first vector field. So charged particles create a vector field in space, and this vector field is called an electric field. And electric fields have a few properties. If the charge creating the field has more charge, then the electric field is stronger. And electric fields get weaker as you move away from that source charge. The structure of the electric field also depends on whether the charge is negative or positive. If it's positive, all the electric field lines point out from the central charge, and if it's negative, all the field lines point into the central charge. I've added for reference just the formula for the electric field, which we don't need to totally understand, but we can look at some key components. We see charge in the numerator, which means electric fields are stronger for bigger charges. We see r squared in the denominator, which means fields are weaker if you're farther away, because r is the distance away. And then we also see this little r hat, which is that unit vector we talked about before, which basically tells us that our vector field points out from the central charge everywhere in space, and in if that q in front were actually negative. So that should all be consistent with our understanding of unit vectors. When another charged particle enters an electric field, it feels a force. And we know that when particles feel forces, they're going to accelerate by Newton's law. And this force can cause a charge to accelerate towards the central charge or away from the central charge along these electric field lines. And the equation that governs this is just that the force is equal to the electric field times the charge. So if the incoming charge is positive, it would get repelled from the central positive charge. And if the incoming charge was negative, it would get attracted towards that central charge. And that should be something maybe you've heard about before. Okay, cool. Another way to frame our understanding of electric forces and movement in electric fields is through a concept called electric potential, which is also sometimes called voltage. And it's a bit more complicated to understand conceptually, but it basically determines how much potential energy a charge would have at a point in an electric field. And it's very similar to, for how we understand gravity, heights above the Earth. If you're higher up above the Earth, you have more energy to fall down, and when you hit the ground, you'll be much faster, as opposed to if you were starting at a lower energy. So for any arrangement of charges, we can kind of draw this map of electric potential lines, and basically they correspond to very similar things to heights above the Earth. So charges at higher potential will have more energy to move. However, unlike gravity, in gravitational fields, everything basically falls down, right? No matter what object you are, you're always going towards the Earth. Because of the fact that we can have positive and negative electric charges, they actually behave differently under the influence of an electric potential. So one rule to just kind of keep in your head is that positive charges move to lower electric potential and negative charges move to higher electric potential. So they basically go opposite directions in an electric potential map. And this should be consistent with our understanding of electric fields, because the charges creating this potential here are both negative, and we can see that the positive charge goes towards the negative charge in the direction of lower electric potential, and the negative charge goes away from the negative charge towards higher electric potential. So you can think of charge movement in electric fields from the field perspective or the electric potential perspective, and we'll do both in this lecture. Now we can get into what kind of materials are affected by electric potentials. So a conductor is a type of material that can conduct electricity. And it can conduct electricity because the charges within the material are allowed to flow freely. One of the most common conductors are metals. In metals, the protons, the positive charges, are bound in place, but the electrons are free to move, so the materials will respond to an electric field. Another example of a conductor is actually a plasma, which is what this course is about. But plasmas are a little bit distinct from metals because in plasmas, both the protons and electrons are flying around independently, and they can actually both respond to the electric field. So both the protons and electrons carry current in a plasma, while only the electrons carry current in a metal. Okay, cool. Now we have to talk about what current actually is. Current is measured as how much charge flows past a given point in a certain unit of time. And the unit for current is amperes. A current happens whenever we apply an electric potential difference or a voltage across some unit of conductor. So if we make one side of the conductor have a positive electric potential and one side of the conductor have a negative electric potential, let's say this is a metal where the electrons are free to flow, the electrons will move to higher potential, as we learned from before, and this results in a net current. One thing that's important to note is that current is always defined as the flow of positive charge. But in some cases, like with metals, only the electrons can move. So the direction of current is actually opposite the flow of electrons. We can see that in this image here. The electrons move to higher electric potential, and the direction of current is opposite the movement of those electrons. So it's a little bit confusing to keep track of. It's just a convention people decided a long time ago. Okay, cool. So that's our intro to electric forces. And yeah, let's just talk about a few ways we see electric forces in our daily lives. Outlets are one really important one. When you plug something into an outlet, it basically applies a voltage or electric potential difference to whatever device you're plugging into it. So this is a common use of voltage. Power lines that we see everywhere are carrying actual current. You might experience static electricity, which is like shocks from everyday objects when they've built up an excess of charge. And one actually really interesting fact is that normal force, which is the force that objects experience when they come in contact with each other. So for example, if you put a book on the table, the book doesn't fall through the table because it experiences a force from the book pushing back up on it. That force is actually fundamentally an electrostatic force because all the electrons in the book are actually repelling all the electrons in the table. So that's why the book doesn't just fall through the table. So all these more complicated forces you might have talked about in your introductory physics classes are actually a result of one of our four fundamental forces. And in a lot of cases, it is the electromagnetic force. Okay, now let's move on to briefly discuss magnetism, which is a little less common, a little harder to wrap our head around, but even more important in the context of plasma physics. Okay, so we're going to introduce another vector field. Now we're going to talk about magnetic fields. In your daily life, you're probably most familiar with things called permanent magnets. Permanent magnets are unique and they're based on materials. And they basically occur due to the spins in the atoms of the materials. So this is kind of more of a quantum effect that we're not really going to get into, but the electrons and the nuclei in atoms have a certain spin, and the electrons also move around the nucleus, which is another form of angular momentum. And both these kind of spin characteristics create like magnetic fields that point in a certain direction. In most materials, these fields are completely random between all the different electrons and neutrons, etc. But in certain types of materials, these spins actually tend to align and they create a net magnetic field. And these type of materials are called ferromagnets. And it's what a lot of permanent magnets are made of. So iron is a common example of a ferromagnet. However, permanent magnets are actually extremely uncommon. They're much less what's talked about in physics and especially plasma physics, because there's another easier way to generate a magnetic field. Basically, any moving charge, any current, creates a magnetic field. These magnetic fields trace circles around whatever the current carrying wire is. And we have a formula here for the magnetic field. And we can basically see that the magnetic field is stronger the more current you have in your wire. And it is also weaker the farther you are away, the greater your R value is. We can see here that our magnetic field is a vector, but I haven't put any unit vector here to show what direction our magnetic field is pointing, because it's a little harder to understand. So in order to get the direction of a magnetic field from a wire, we have to use something called a right-hand rule. And it's basically a trick that you can do with your hands to basically figure out where a magnetic field is pointing. So basically what you do is you put your thumb in the direction of the current, and then your fingertips just curl around in the direction of the magnetic field. So they basically trace circles around the current to tell you which direction your magnetic field is going. So this is a useful trick that you might have to use in a physics class in the future. But the main lesson is that the magnetic field lines wrap in circles around the current carrying wire. It doesn't go straight out like for our electric forces. Just like we had electric fields and electric forces, we also have magnetic forces. So if a charge moves within a magnetic field, it experiences a force. And this force is actually governed by a cross product, which is something we talked about earlier. So basically we can see that the force comes from a cross product between the particle velocity and the particle magnetic field. And that automatically tells us a few interesting features about the magnetic force. First, the magnetic field and the velocity cannot be parallel. If they're parallel, that cross product is just zero and there's no force. It also tells us something about the direction of the resulting force. Because it comes from a cross product, the force, the new vector, must be perpendicular to both the original vectors. So the force on a charge will be perpendicular to both the original velocity and the magnetic field. And because of that fact that we have two vectors and another vector perpendicular to it, it becomes really hard to understand in 2 dimensions on a flat piece of paper or a slide. So we use these helpful symbols to show what it means if something is going like into the page or slide or out of the page or slide. So you can think of it like a bow and arrow. If the magnetic field is out of the page, it looks kind of like a bullseye or the tip of the arrow poking through the page. And then if the magnetic field is into the page or slide, we use an X, which you can think of as the back of the tail of the arrow. So it's just something useful to keep track of to know what directions people mean in different physics problems or scenarios. Okay, cool. Sometimes it's hard to just figure out the direction of your resulting vector in your head when you're doing a cross product. So for that, we have another right-hand rule, which is a little trickier. For this one, you point your pointer finger in the direction of the particle velocity. Then you point your middle finger in the direction of the magnetic field. Sorry, it's a little hard to see here. And then your thumb will automatically point in the correct direction of the force. So you can also use this when problem solving to figure out what the final force on your particle will be. Okay, cool. So let's use the new right-hand rules we've learned and also our symbols for the magnetic field to figure out how a particle will move in a magnetic field. So let's say we have a magnetic field into the slide or into the page, and then we have a particle that's moving up with some initial velocity. I'm not going to do it here because it's kind of hard to see the slide, but if you did your right-hand rule with this velocity and this magnetic field, you would find that the force on the particle is going towards the middle of the slide. And if you apply a force towards the middle of the slide and the particle is moving up, it's going to start to turn and it will end up on the top of the slide. Then we can repeat this process with our same magnetic field and our new velocity direction, and we find that the new force on the particle is down. So if it's moving left and then it's forced down, it's going to end up on the left-hand side of the page. And we can do this again, compute the new force vector, which again is towards the middle of the page. We end up at the bottom, and we repeat this one more time, and it turns out that we end up right back where we started. So this is just a toy problem that shows when we put a charge in a constant magnetic field, it will move in a circle, which is a really important feature of magnetism. And if we put a negative charge there instead, it would also move in a circle, but it would just go in the opposite direction. So it would move clockwise rather than counterclockwise. So this is a really important feature of motion to understand. And we can kind of connect this back to something you may have learned in a physics class if you've taken an introductory physics class before. You might have learned about central forces and how they can cause centripetal motion. So for example, if you have your keys on a lanyard and you swing your lanyard, the tension force in the lanyard causes the keys to move in a circle. That's an example of centripetal motion. Magnetic fields act extremely similarly. The magnetic force acts like the tension force of the lanyard on your keys, and it causes the particles to rotate in circles. So it's a very similar concept, and you can use very similar equations to govern both kinds of motion. In the past examples, let's go back a sec. We imagined that the original velocity of the particle was perpendicular to the magnetic field. But we didn't consider what if the original velocity is parallel to the background magnetic field? What would happen in that case? Well, we know the magnetic force is a cross product between the velocity and the magnetic field. So if the velocity and the magnetic field are parallel, the force is zero. If the force is zero, the particle is not going to accelerate, and it's going to maintain its original velocity. It will keep going at the same speed and the same direction. So particles moving parallel to a magnetic field feel no force and keep moving along with the constant velocity. So we've looked at two specific cases if your initial velocity is completely perpendicular or completely parallel to the background magnetic field. However, in real life, things are rarely oriented that perfectly. So in many cases, when you turn on your magnetic field, your particle will be moving at some angle with respect to that background field. That means part of its motion will cause that spinning we talked about before, and the motion parallel to the magnetic field will be unchanged. And what happens is actually that the particle will trace out this helix pattern we see on the slide, where basically it's going in circles, but it's continuing to move up parallel to the field line. And this phenomenon is called gyromotion, and it's what basically all of our particles are doing in a plasma when we apply a magnetic field. They rotate around the field and move parallel to the magnetic field lines. One, I guess, more philosophical question about magnetic fields that you might be thinking about. For electric fields, there was a clear source. We had a charge and all the electric field lines pointed outwards from that charge. It was producing the field. And we might wonder if there's something similar for a magnetic field. Is there a magnetic charge? And the answer from what we know so far is no. Magnetic field lines can't all point out from one point in space. Even for a permanent magnet, which we can see here, the magnetic field lines come out of one end of the magnet and then loop back into the other. There's no net flow of field out of the permanent magnet. If some scientists are trying to discover some sort of magnetic charge that can produce magnetic field lines pointing outwards from it, if it did, it would be really interesting for electromagnetic theory, but so far has not been discovered. And this is what is often called, there are no magnetic monopoles. There are no sources of magnetic field, only dipole fields where the field lines come out from one end and back in the other. Okay, cool. This is another kind of side tangent of a fact that I think is really cool, which is how special relativity ties into electromagnetism. So special relativity is a really interesting phenomenon that happens in physics, which is due to the fact that nothing in the world can move faster than the speed of light. It's a universal speed limit. And this results in really weird effects when you try to move close to the speed of light. So let me give one example of that weird effect. If we're at rest and we look at a ruler, we will measure the ruler to be 12 inches. However, if we were moving at 80% of the speed of light past that same ruler and we tried to measure it, that ruler would actually only be 7.2 inches. Lengths are shorter if you're moving quickly by them, which is like a very weird, quirky physics phenomenon. And special relativity actually plays a big role in electromagnetism as well. We talked about electric and magnetic fields as if they're totally different. They have different equations, they come about in different ways. But using the theory of special relativity, we actually realized that electric and magnetic fields are sort of the same thing. So as an example, if we're at rest and we observe a positive charge at rest, right, we will see that charge producing an electric field. But there will be no magnetic fields because there's no current. And we know magnetic fields come from currents. However, imagine we're moving really, really fast past that charge. Then, from our perspective, that charge is actually moving, it's a current, and when we see that current, it will be producing a magnetic field. So depending on which reference frame you're in, you will actually see just an electric field or a combination of electric and magnetic fields. So these fields can transform into one another through special relativity, which is a really interesting symmetry that we find in physics, although usually not super relevant for plasma physics. Now that we've talked about both electricity and magnetism in isolation, we're going to talk about how they interact and affect one another, because usually they're not seen totally by themselves. In order to do that, we need to learn one more definition, which is the definition of magnetic flux. Magnetic flux is basically a measure of how much a magnetic field penetrates through a given surface. So the magnetic flux is a function of the area of the surface, and it also comes from a dot product between the magnetic field and a unit vector, that little n hat, that points perpendicular to the surface. So magnetic flux is really large if the magnetic field is perpendicular to the surface, poking through it, and magnetic flux is 0 if the magnetic field is parallel to the surface. And if it's somewhere in between, if it's poking through the surface at an angle, you'll have just a slightly smaller magnetic flux. So it's basically a measure of how much your field goes through a given surface. And magnetic flux is important because it shows up in a very important law, which is known as Faraday's law. And it basically tells us that if the magnetic flux through a surface changes in time, that creates an electric potential or a voltage. So earlier in this lecture, we talked about how voltages are created by electric fields, which are always created by electric charges. But that's actually not true. You can also create a voltage or electric potential out of thin air simply by creating a changing magnetic flux. And that resulting voltage can be used to create a current, basically out of nowhere. So this is very, very cool, and it's one of the key links between magnetic fields and electric fields. So let's go through an example of how this might work. Imagine we have two loops of wire nested within one another. If we put a current in the inner loop, that will create a magnetic field pointing upwards through that center loop. Then let's imagine we change that current. We decrease the current in the inner loop. That creates a changing magnetic flux through the outer red loop, right? The outer red loop sees less magnetic flux than it did before. And because of that, an electric potential is going to be induced in that outer loop, which just creates a current in that outer loop, even though there wasn't one before. So it's almost like magic. One important thing we have to think about is what direction will the new current go? And that comes down to this negative sign that we can see in Faraday's law, which is also given a name. It's called Lenz's law. And the negative sign tells us that the direction of the induced current is going to be such that it counteracts whatever change in magnetic flux occurred. So nature basically wants things to go back to how they were. So Faraday's law will generate a new current that counteracts whatever change has happened. So let's walk through another example, very similar to the one we just did, and try to predict what direction the current will flow in the outer loop. So we have the inner loop with some fixed current creating a magnetic field. And then let's say we increase the current in that inner loop. So we have more magnetic flux through the outer loop. The current induced in the outer loop will try to counteract this change. So the outer loop is going to get a current in the opposite direction that creates a magnetic field in the opposite direction. And that will work to oppose the original change that happened. It will work to bring the magnetic field back down to what it was before. So that's how you can always figure out the direction of your induced current. It's whatever direction would bring the system back to how it looked before the change in flux. Faraday's law is absolutely everywhere in nature and in technology. One example of a device that uses Faraday's law is a generator. If you've ever used a generator to power your house, it actually contains a magnet that moves around in circles, creates a changing magnetic flux through a coil, and that is what generates the electricity or the current that then can go into your house. Another example is the current in power lines. Normally, if you put current in power lines, it would decay over time because of the resistance of the wires. However, what our power lines use is something called alternating current, which is a current that changes over time. And due to Faraday's law, that changing current creates changing magnetic fields, which then induce more current due to Faraday's law, and that's what allows the current to travel for really long distances without dying out, because Faraday's law is always generating new fields to keep it going. Very similarly, light waves, so all the light that lets us see things in the world, right, is called electromagnetic radiation. And that's because it is composed of oscillating electric and magnetic fields that sustain each other through Faraday's law. So basically everything we use comes from Faraday's law. Okay, cool. So now we've gone through basically most of the core principles of electromagnetism you might encounter in an introductory physics class. And now we're going to do a little sneak peek of how these phenomena relate to plasma physics, which is one of the central topics of this course on fusion. So for starters, we talked a lot about plasma, or what it is, in our first two lectures, but we never really talked about how to get a plasma state. So normally our atoms are composed of electrons in orbitals around our central positively charged nucleus. And to get a plasma, we need those charges to be moving totally independently. One way to do that, and how a lot of people do that every day, is basically you inject a bunch of gas, neutral gases that have structures like this, into a chamber, and then you apply a really strong electric field to that neutral gas. So let's imagine we apply a downward electric field. We learned before that positive and negative charges respond oppositely to applied electric fields. The positive charges move along the field, and the negative charges move against the field. So the proton and the electron will experience opposite forces, which cause them to accelerate away from each other until they're completely independent. So in fusion devices, this is one of the main ways we make plasma, is we apply an electric field to the plasma that rips the protons and electrons apart so that they act independent. Here's another scenario. What if we apply an electric field to a plasma that already exists? How will the plasma behave? Well, in a plasma is a conductor. It has free positive and negative charges, both are which are free to flow. So when you apply an electric field to a plasma, it will feel a force. The positive charges will go with the field, the negative charges will go against the field. And once we have that buildup of charge, that actually creates a new electric field that points in the opposite direction. And that cancels out the original electric field, right? Because the charges have oriented themselves to cancel out that original field. So a common feature of plasmas is that they shield electric fields. If you apply an electric field to a plasma, it rearranges itself until the field is gone, which is also true of other conductors like metals. What about plasma motion and magnetic fields? This is a bit more complicated, but we can think back to when we talked about single particle motion in magnetic fields. We know that if we have some initial plasma state where all the charges are moving in different directions, when we turn on that magnetic field, the particles will have unique motion perpendicular and parallel to the field. In the perpendicular direction, they'll spin around in circles, and in the parallel direction, they'll move along the magnetic field. So we get this gyro motion that we talked about before. And what's really interesting about this is it means that if you apply a magnetic field to the plasma, it's very, very easy for the plasma to move along the magnetic fields, but very hard for the plasma to move across magnetic fields. Because as soon as it starts to move perpendicular to the field, it experiences a force that makes it turn around and rotate, as opposed to being able to have net movement perpendicular to the magnetic field. So this governs a lot of how humans have tried to confine plasmas on Earth. We use these magnetic fields to constrain the direction of plasma motion because the plasmas have a really hard time moving across the magnetic field. And we'll talk about that more in future lectures. One example of this sort of plasma motion in magnetic fields in nature is the aurora borealis. Essentially what happens here is the sun emits streams of plasma or charged particles towards the Earth. And as you might know, the Earth actually has a magnetic field. So it has these magnetic field lines that come out from the top and into the south pole of the Earth. And particles can actually get trapped in that magnetic field, doing the sort of gyro motion we discussed before. And when they become trapped in the Earth's magnetic fields, they interact with all the molecules in the Earth's atmosphere, and that's actually what causes the really pretty light emission we see in the aurora. It's due to particle trapping in the Earth's magnetic field. Okay, finally, now that we know a lot about electromagnetism and plasma motion in electromagnetism, we can think about how we can leverage these forces to confine plasmas and make fusion on Earth. So let's first think about what our options are for confining plasma on Earth. I guess the first thing to think about is the most successful fusion device, which is the sun and the stars. Stars are really, really good at fusion, and they actually use gravity to keep the plasma together and keep the fusion reaction going. However, as you might remember from our discussion of fundamental forces, gravity is by far the weakest fundamental force. And the only reason it works to do fusion in the stars is because the stars are enormous. So it applies a big enough force just because of the mass of the sun, but in reality, the gravitational force is very weak. We can't make something nearly as big as the sun on Earth, so we're going to need to rely on a stronger force to confine our plasmas. The main option for this that a lot of people pursue is using electromagnetic forces. Electromagnetic forces are the natural choice because we're working with a charged gas, the plasma. So we know it's very, very responsive to electric and magnetic fields. So what everyone here is doing at the Columbia Plasma Physics Lab is working on how to confine a plasma using electromagnetic forces. One example of that is a device called a tokamak. We'll have tokamak specific lectures coming up where we talk about this very specific type of fusion device. But we can see a quick overview here. And basically everything you see in this picture is a giant magnet or a giant wire. We have the big gray magnets around the outside, the blue circles are magnets, the green thing in the middle is a magnet, and then the plasma itself, shown in pink, basically acts like a wire carrying current in our tokamak. So we'll go through a few of those components here. First, we have what's called our toroidal field coils, which are the biggest coils, and we have several of them going around the device. And these coils all carry a current, and that current creates a magnetic field that wraps the long way around the donut. So this is the main confining magnetic field for our plasma. We also saw that magnet in the center of the tokamak or donut. This is called the central solenoid, and the central solenoid uses Faraday's law to create a current in the plasma itself. So just like the example we did with the two wires, the solenoid creates a changing magnetic flux through the tokamak, and that changing magnetic flux through Faraday's law creates a voltage, which then actually drives a current in the plasma. So this is a very clear application of Faraday's law in plasma physics. Finally, we have our colloidal field coils, which were the final coils around the side of the device. And these also carry current and create more unique shapes of magnetic fields. And because the plasma is full of basically moving charges, moving current, they respond to these externally created magnetic fields. And these extra magnetic fields can be used to push or pull the plasma. So they're actually used to make the plasma into different shapes by attracting or repelling different charges. So these are very important as well. All right, that's all we have today discussing electromagnetism, but our next lecture will be really getting into plasma dynamics and how plasmas move and operate within complicated electric and magnetic fields. So we look forward to seeing you then. Thank you.